Yes, hello class. This is the 2.5 video and we talk about continuity, determining whether a function is continuous at a point on this graph. Okay. Now our objectives are the following. We'll determine where in the domain of a function that could be a polynomial or a trigonometric function, exponential function, whatever it is. And so in this domain, we want to know where it is continuous and where it is discontinuous. And then we also talk about the intermediate value theorem. We call it the IVT. And then we use this theorem to search for the root or solution toward equations. Okay, so let's begin with the first defining what continuity or continuous of function, what it means. Okay, the limit to a function as x approaches a certain value a can often be found simply by calculating the value of the function at that a, if it's in the domain. So functions with this property are called what? Continuous at what? At a. It is in the domain, so we can find that. Okay, we will see that the mathematical definition of continuity corresponds closely with the meaning of the word continuity in everyday language. A continuous process is one that takes place gradually without interrupting or abrupt or change. So to define a function, the first definition we'll look at is that a function f is continuous at a number a if the limit as the function, there's a two-sided limit, is equal to what? The function value at a. Okay. Now, this theorem can be broken down into what? Three parts, which we will call the continuous test, or continuity test. So if you're given any function and you want to test whether it is continuous, we do the following three things. Okay, you find the function value at a. So if the function is continuous at a value a, then a, remember, is in what? Is in the domain of the function. And then the limit as if x approaches a exists, and then they are what? They are equal. Okay, so the function value at a, the limit, there's a two-sided limit. Okay, as x approaches a exists, and then they are also equal. Now, when you have this, then this we say that this is what? It is continuous. The function is continuous at a. Okay, the definition says that f is continuous at a if f of x approaches f of a as x approaches a. Thus, a continuous function of f has the property that a small change in x produces only a small change in what? In f as a function. Now, in fact, the change in f of s can be kept as small as we please by keeping the change in x sufficiently what? Small. Okay. Now, if f is defined near a, that is x is approaching, as x approaches a, it is defined. In other words, f is defined on an what? Open interval. Okay. Now remember, the open intervals are something like what? A, b, it is open. Okay. Or you can have brackets on 1 and then b, that's an open interval. You can have for infinity, negative infinity, net a, that's also an open interval. So we say that f is defined on an open interval containing a, except perhaps at a. We say that this function, f is what? It is continuous order at a. Okay. Or we simply say that f has a discontinuity at a if f is not continuous at a. So if it is continuous, we say that it is continuous, that the function is continuous at a. If it is not defined over the interval, then we say that it is what? Discontinuous. Okay. In several physical phenomena are usually continuous. For example, the displacement of or the velocity of a vehicle as it varies continuously over time. Okay, or your height or my weight, we say these are continuous what? variables. But if we have something like electric current, there could be discontinuities there. Okay, so we have places that we can apply this in our life. Anyway, let's think of it geometrically. That if I'm drawing a curve like this, if I draw a curve without, removing my hand, then we say that is continuous. But if I'm drawing a curve, once I take my hand and jump, there's discontinuity at this point. So here we say that you think of a function that is continuous at every number in an interval as a function whose graph has no break in it. Okay, the graph can be drawn without removing your pen from what? From the paper. Okay, so the first one I did here, this is continuous, that is not continuous. Because as I'm drawing this curve, I have to remove my pen, and then once I do that, there's a what? There's a gap, there's a break in the what? The flow of the graph or the curve. So therefore, it is not continuous at that point. Okay, now let's take a graph example. We want to determine where this function f, okay, is discontinuous. Where there's a hole, okay, where there's a break, where there's a jump, these are all what? It is discontinuous. So where you have breaks, you have jumps, okay, or you have gaps, okay, where you have gaps too, they are what? Or you have a hole, sorry, you have a hole, that is what? That's all in the graph, that is what? Discontinuous. So if you look at this graph carefully, okay, look at where 1, look at 3, and look at what? 5. Okay, we could say that the function f, okay, is what? Discontinuous at what? X equal to 1, 3, and what? And 5. Okay, X equal to 1, 3, and 5. Otherwise, this is what? It is what? Continuous. Why? Because there is what? Here there's a break, there's a hole, and then at 3, there's a what? A jump, and then there's a hole at this place. Okay, so what you say is that in this case, at each of these values, okay, for example, at x approaches 1, of the function is not the same as what? F at what? At 1. Okay, now similarly, you can say that the limit x approaches 3 of the function is not equal to the function value at 1. Function value at 3. And then the limit x approaches 5 of the function is not the same as what? The function value at what? 5. In this case here, the function value is, which is, I don't know the value, but it exists, okay, but the limit also exists, but they are not what? They are not equal. Okay, so in this case, again, f is discontinuous at what? These values of what? These values of x. Okay, now, there are other examples where you have a function which is given by this. This is what we call the greatest integer what? Function. Okay, so f of x has what? Discontinuity at all the integers, because the limit as x gets to n, it doesn't exist. Now look at it. Okay, consider the integer at what? 1. Okay, as you approach the limit, it's as x approaches 1 from the left, what happens to the f of x? It is equal to what? 0, right? But the limit x approaches what? 1 from the right, or the function is actually equal to 1. Now you see that this limit x approaches 1 of the function does not what? Exist, because these two are not equal. 0 is never equal to 1. Okay, so at each of the integers, 0, 1, 2, 3, it doesn't exist there. Therefore, this is what it is discontinuous. Okay, the function is discontinuous at what? Every integer. Okay. Now, again, the function is the continuity in this part we call this what? The jump what? Continuities. Jump continuities. The next example, okay, we'll explain the graph in a minute, but let's see how do we work. If you look at the function x is equal to negative, it's not equal to 2, and x is equal to 2, it means that something is happening at 2. Okay, so we want to find whether this is what continuous or not, right? Okay, so first let's do the test. The continuity test. Say that the first is that what is f of what? Let's say that is near x equal to what? 2. Okay, so let's find f of 2. What is f of 2? According to the function, f of 2 is 1. Okay, if x is equal to 2, the value is 1. Okay, 2. What's the limit? X goes toward 1 of the function. Okay, so we have the limit x goes toward 1, sorry, not 1, 2. Okay, of the function is what? X squared minus x minus 2 over what? X minus 2. We cannot use the direct substitution, so we need to simplify that. Then when you simplify, you have the limit x goes toward 2, which is x minus 2, and then x plus what? Plus 1, divided by x minus 2. So this is equal to the limit x goes to 2 of x plus what? 1. That gives me 2 plus 1, that is what? That is 3. Okay, now the third test is that these must be equal, that the limit x approaches a of the function must equal to the function value at a. Now we know that this is equal to 1, and that is equal to what? 3, and these are not equal. So we can say that f is what? Discontinuous at what? X equal to 2. Okay, now if you look at the graph, okay, the function value at what? 2 is 1. The function value at the limits, okay, of 2 is what? Is basically what? Is 3. And there's a jump, or there's a hole in the graph. That is why it is a straight line, because when you simplify this expression, this is basically what? 1 plus 1. So that is what, like 1 equal to x plus 1. Okay, so it goes up by 1. Okay, that's what it is. All right, so it is discontinuous. This type of discontinuity is called infinite what? Discontinuity. Okay, now let's go to other definitions. We can define this continuity in terms of what? One-sided limits. Okay, so we can say that a function f is continuous from the right, that is the right hand limit, okay, if the right hand limit is equal to the function value at a. And then similarly, if f is continuous from the left, then the left hand limit must equal the function value at a. Now remember, generally the limit x approaches a of the function, if it is equal to what? A, then we say that f is what? Continuous. So that is good to know. So that's the second definition. The third one is what? In terms of what? Interval. That if I say that, if I give you the interval AB, okay, and I say that f is continuous on this interval, then it means that if I pick any value within the interval, the function must be continuous at that point. Okay, that's what this definition talks about. Okay, that's all it is. So if I consider an interval like what? 1 and 2, and I said the sensory function is continuous on this interval, then any value that I pick within 1 and 2, the function must be continuous at that value. Okay, and that makes sense because if I have a graph like this and I have this curve, okay, and this is my 1 and that is 2. Now, if it is continuous, then of course within this interval, there shouldn't be any hole or any jump or gap between the x between 1 and 2. Okay, so now let us take this example. This is actually exercise number 45 from the textbook. It says that for what values, okay, it should be what value or values, sometimes you can have more than one. What value or values of the constant c in the function f, okay, is the function f for continuous. Now, this is a piecewise function. Therefore, to do that, if you look at x is to the left of 2 and to the right of 2. Now, if this function is continuous, then it must be continuous at 2. And what do we mean? It means that the left hand and the right hand limits are equal. Okay? So that will help us to find this. So it means that we need to find this, the limits x approaches 2 from the left of the function. It must equal to the limits x approaches 2 from the right of the same function f of x. Now, if I go here, if I look at the left, then I'm talking about this part, the top part. So this is the limit x approaches 2 of cx squared plus 2x. It must be equal to the limit x approaches 2 of f of x, which is the bottom part, x cubed minus cx. Now, both of these are polynomials, and you know polynomial, the domain is all real numbers, right? So if we see 2 is a real number, therefore it must be continuous there. So we can use the direct substitution again. See the importance of the direct substitution. So if I substitute 2 for x, then I have c times 2 squared plus 2 times 2 is equal to 2 to the third minus c times 2. Okay, so this will give me 4c plus 4 equal to 8 minus 2c. Then we add 2c to both sides. That gives me 6c plus 4 equal to 8. Okay, then I have 6c is equal to 4. When you subtract 4 from both sides and divide both sides by 6, we have c is equal to 2 over 3. So it means that the function f, it means, okay, f is continuous at At 2. When c is equal to 2 over 1. That'll be your answer. All right. Let's solve another example. Okay, this is one of the examples in the textbook. I believe it's in this section 2.5. I think it says maybe example 4 or 5. I'm not sure. Okay. It said we are given the function f of x is equal to that. We're saying that a function is it is continuous on the interval. Okay. On the interval -1 to +1 inclusive. Okay. So to solve this, right, we want to show that it is continuous. Okay. To solve this, first, we know our f of x. We will consider a between this interval -1 and 1. Remember, if it is continuous on open interval, it means that if you pick any value within the interval, it must be continuous. Okay, so if it is continuous, what do we mean? Okay, so if f is continuous, okay, then this, we use the test. It means that f of a is equal to the limit x approaches a of the function, and this limit exists. So first, let's find f of what? F of a from this, where f of s is equal to that. Okay, well, f of s is that. So this gives me 1 minus the square root of what? 1 minus a squared. And then let us all find the limit x approaches what? A, right, of the function f of x. Okay, now this is equal to the limit x goes to what? A, okay, of the function 1 minus the square root of 1 minus x what? X squared. Okay, now this is equal to the limit x goes to a of 1 minus the limit x goes to a of what? The square root of 1 minus x squared. Now I'm using law number 2, difference. Then law number 6, which is the 7 actually, that the limit of a constant is a constant. So this is what? 1 minus the square root of, okay, 1 minus what? A squared. Now look at this expression here, and look at this expression here. See that they are equal. So it means that this is true. Therefore, okay, therefore we say that, in fact, f is what? Continuous. F is continuous on what? Interval. Period. That's it. Okay. And we are almost kind of done here. There should be one more very important theorem, that is the intermediate value theorem. But let us consider continuity of the sum, difference, the product, and quotient. Remember the laws of limits that we did in the previous video. Okay, so if the two functions f and g, they are continuous at a, okay, and then c is a constant. What that means is that the limit as x approaches a of f, okay, is equal to f of a, and then the other one, the limit x approaches a of what? G of x is equal to, g of a. So it means that it is continuous. That's what this part, the first part means. Then the following are what? Are also continuous at a. Then when you add them, the sum of the two is continuous. The difference will also be continuous at a. The what? This constant times the function, f or g, will also be continuous, and then the quotient will also be continuous, provided the g of a is not what? 0. Okay. So continuous functions as a linear, the sum, and then the product and all that. And the next one is about composite word functions, and generally speaking, polynomials in their domain. All right. So this is a theorem, says that the following types of functions are continuous at every number in their domains. Okay, polynomials, trig functions, exponential functions. Remember, exponential functions are this, and the domain is also all real numbers, right? Because the graph looks like that. Okay, so the rational functions, inverse trig function, and logarithmic word functions. All right, so their domain. The next one is about what? Composite functions. So it's saying that if a function f is continuous at b, And then as x approaches a of the function is also equal to b, then we can say that the composite function is what is continuous, because the limit as x approaches a of the composite function f of g is equal to f of b. Okay, in other words, this is what? This is true. Okay, so let's evaluate the function, apply this. Here's an example. Okay, so this is the next theorem is stating the same thing. Okay, only that it's just making it more general. So I want to evaluate this function. Okay, I'm going to use the composite functions for that. Now I'm going to let my f of x be equal to this. Okay, which is what? The sine of pi by 2 cosine of what? Tangent of x. Okay, so if I want to evaluate this, I want to know whether it is continuous at 0, right? As we have there. So the question that is f continuous at 0? Okay, it's a question. So first, let's find what is f of 0. F of 0 means that this is sine of what? Pi over 2 cosine of tangent of what? 0. 0 is in the domain. Now, what is tan 0? Tan 0 is what? 0. So we get pi over 2 cosine of what? 0. Now, what is cosine of 0 is 1. So this is going to be a sine of what? Pi by 2 times what? Times 1 is times 1. Okay, so that gives me sine of what? Sine of pi by 2. Sine of pi by 2 is what? Is 1. Okay, now let's consider the limit. The limit x approaches was 0 of the same function f of x. Okay, now notice that 0 is in the domain of sine, cosine, and then also tangent. So 0 is in the domain of the sine, cosine, and then the tangent functions here. Okay, tangent. All right. So if you want to find this, then this is equal to the limit x approaches 0 of, just like what we did there, pi over 2 cosine of tangent of x. Now, since x is in the domain, we'll use a direct substitution, which will give us the limit, okay, x approaches 0. Sorry, this will just be a sine of what? Pi over 2 times the cosine of what? 0, because tan 0 is 0. And again, just like we did, this is sine pi over what? 2. The sine of 0 is also what? Is 1. So this is times 1. And then we have what? Finally, we have sine of pi by 2, which is 1. So you see that they are the same. And therefore, the answer to this question is what? Is 1. And we can say that f is what? Yes, f is what? Continuous at 1, at 0. And finally, we have our what? Intermediate value theory. Okay, it says that, now let me give you a quick background here. Intermediate value theorem is, so you remember your calculator, they give you, sometimes they give you a function and they ask you to find the root or the solution to this function. Now, if you can search in around a certain interval, and you know that if you draw the graph and it crosses the x-axis, that means that intercept, x-intercept is what? It's a 0. Now, if you don't know it and you have the interval, you can get a range and then zoom in and be able to detect what? That value. Now, you can start it by applying this theory. then you can set for it. So for example, says that this is a definition. Suppose that f is continuous on a closed interval, which is like this. And let n be any number between the function values at what? The endpoints of the closed interval, where these are not the same. In other words, they are not equal. Sometimes if you are looking for specific for 0, then you can say that if it is 0, because if you have, if you have 0 here, then one of them must be positive and the other must be what? Negative. So because you're going to find the equation s equal to 0, right? The function is equal to 0. So if it's equal to 0, then you want to say that the function values will have what? Opposite signs. Okay. If this situation is true, then you can say that there is a c in the interval a and b such that the function value of c is equal to what? The n. Okay. So if it is equal to the n, if n is 0, in this case, this is be what? This is my n. Then I can say that this is equal to 0. Therefore, I can find the root of the what? Or the solution to the function. Okay. I mean, graphically, this is what is happening. So this is my f of x, and my function value at a, the endpoints a and b are the following. Okay. So if they are different, they are not equal, then there is what? A c such that the function value, okay, is equal to what? Is equal to a. And this is the diagrams that we can get for that. Okay, either this or that. So let's take an example. It says that use the intermediate value theorem to show that there is a root or there's a solution of the given equation in the what? The specified what? Interval. Okay. So we have this function, this equation here. Now we're going to write this as what? Natural log of x. It is equal to this x minus the square root of x, right? So what we do is that we don't know our function, so we're going to equate it to 0. Excuse me. So this is a natural log of x minus, sorry. Let me get my, that's not what I wanted to do. Okay, so the function, we want to know our function. So they have natural log of x, okay, is equal to, this is the equation, square root of x. Okay, we write this as what? Natural log of x, bring all to one side. So minus x plus square root of x is equal to 0. So in this case, according to the intermediate value theorem, my n is what? N is equal to 0 in this case. So we want to find the root. Okay, we are given the interval. My a is what? 2. My b is what? My b is equal to what? 3. Okay, so a is equal to 2, b is equal to 3. So first, let's find the function value of a, that is f of what? F of 2. By the way, this is my f of x. So my f of x is what? The natural log of x minus x plus the square root of what? X. So what is f of 2? F of 2 is a natural log of 2 minus 2 plus what? Square root of what? 2. Okay. Now, if we evaluate this, this is, I get natural log. It will give me, I think I have the, okay. The first one is this, if you evaluate it, this will be 0.107. Okay, then also let us find f, the function value at 3, which is natural log of 3 minus 3 plus the square root of 3. Now this is equal to what? Negative 0.169. Now, as we can see, f of a is not equal to f of 4b. In other words, f of 2 is not equal to f of 4, f of 3. So what it means is that since this is the case, okay, since these have opposite signs, since they have what? Opposite what? Signs, there is a root, okay, there is a C, okay, there's a C in the interval given 2, 3, such that the f of C is equal to what? 0. Okay, so that brings us the end of it. Okay, so thank you. This is the end of this section. The last one will follow suit. Take care. Bye-bye.